Good day, sir. My name is Mr. Kovan, and today I'll be presenting about the automatic voltage control of a computer fan using a buck converter. So now let's look at the overview of this entire project. So here, what's needed is to get the constant output voltage of 9 volts at the output of a buck converter. So I'll be using a variable input voltage. So this input voltage will be varying between 15 to 25, but as we need the constant output at the end of the buck converter. So I'll be switching the buck converter using a MOSFET, and I'll be controlling that MOSFET by a PWM signal. So in order to get the constant output of 9 volts, I'll have to implement the PI control that will change the duty cycle of the PWM. So we'll be using the high side switch, so I will need the bootstrap on a gate drive. So I'll be using the gate drive because of the signal that is coming from the PWM control is very less to switch on the gate, the MOSFET. So we'll need the gate drive to boost up that signal so it can be able to switch on and off the MOSFET. So now let's look at the problem statement. Then the computer fan needs to run at the constant speed while the voltage is increasing and decreasing. So in order to get the constant speed of the fan, the constant voltage is needed at the output of the buck converter. So I will be designing the buck converter circuit where automatic voltage control is on a fan when the input voltage varies. So let's now look at the specification. Here are some requirements for this project. So we'll be needing a input voltage, a variable input voltage that will be varying from 15 volts to 25 volts, a buck converter that will need a 9 volts output voltage. Then here are some specification for a fan. So this is a computer fan that ranges from that works with 12 volts. It's a simple fan. Then let's look at the PWM specification. So we need the switching frequency of 10 kilohertz with a minimum duty cycle of 25% and maximum duty cycle of 75%. So let's now look at the literature review. So when we're looking at the literature review, we know that we have two 555 timers. So the first 555 timer is a stable. It has 2 capacitors and 2 resistors. So on this A stable will be generating our frequency, our switching frequency. Then on the second one, the second 555 timer is a monostable, whereby we'll be generating our duty cycle using this capacitor and this resistor. So there are some formulas for it. I will show you as time goes. So here we have a gate drive with bootstrap. So a gate drive with bootstrap. A bootstrap is used when we're using the high side switching. So this gate drive is used when to boost up the signal that is from PWM, so that can be able to switch the MOSFET. Then this is the PI control. PI control is a feedback control loop. Actually, this one is a feedback control loop that calculates an error signal by taking the difference between the output of the systems. So let's now look at the design process. So here on my design process, so first of all I have to conduct the research of the buck converters, gate drive, PWM, PI control. So all I needed is time, because time is some of my constraints that I faced. Time management. So I had to do some schedules and I had to stick to times. Then also accuracy when doing calculations, like doing calculation for buck converter and for the gate drive, those capacitors, and cost, because some of these components are so expensive. So some burn easily, so I have to catch a taxi to go buy some. So yeah, those are my constraints that I faced, but I was able to overcome them. So yeah, let's look at the block diagram. So here's the block diagram. As we can see, the input voltage ranges from 15 volts to 25 volts, which is sent to the buck converter, and the buck converter have to give us the output voltage of 9 volts. So in case if the output voltage is not 9 volts, the comparator amplifier will calculate the error and will send it to the PWM, and the PWM will change its duty cycle and give it back to the buck converter. So in order to get this, so as we can see here, our gate drive with bootstrap, it's supplied with 12 volts and our PWM signal is supplied with 5 volts. So let's look at this again, the PWM control. So here we calculated the switching frequency using these two capacitors, these two resistors and a capacitor. So as we can see, we use this formula, say 1.44 divided by R1 plus 2 times R1 multiplied by C. Then on our monostable, so we got our duty cycle, which will be changed. So we see I selected the capacitor of 100 nanofarads, so and designed this resistor of 12 kilo ohms. Then let's look at the bootstrapped gate drive and a buck converter. So here we have our gate drive with our bootstrap. So here we calculated the bootstrap capacitor, which is 10 times this capacitor here. So here this gate drive is used to boost up the signal that is from the PWM, from our PWM signal, which will be put on the pin 10 and will be get out through pin 7 to our MOSFET. So this thing boosts up the signal because the signal from the PWM is very low to switch the MOSFET. So we use the gate drive to switch. So the bootstrap, this bootstrap capacitor, it's used to we use it when we are using the high side switch. So yeah, so let's look at the buck converter. So here is a buck converter and it's connected with the voltmeter. So here we have 80 ohms. This 80 ohms is just equivalent resistance of the fan. So I couldn't get a fan on Proteus. So I calculated this buck converter capacitor using this formula here. So here, if we look to go back to the bootstrap capacitor, I use the total charge over V boot. So the total charge formula here is it's a gate drive times all these currents times time on times the charge of LS. So let's look at the PI control. So the PI control here, I needed 9 volts at output. So when the output voltage is 9 volts, I'll have to get 5 volts as my output, which will be fed to my comparator. Then the proportional value KP is calculated by using the RF, which is a feedback resistor, over R9, and my integral value here is calculated by 1 over R9 times C7. C7 is this 1 microfarad. So here let's look at our result, what we get. So this is a buck converter output waveform when the input voltage is at maximum of 25 volts. So as we can see here, it has some ripples. So let's look at the monostable output waveform when the input voltage is 15. So we can see that when the input voltage is at 15, it's at its lowest input voltage. So we can see that the duty cycle is high, and then when the monostable output, let's look at the monostable output when the input voltage is at 20 volts. So we can see that the voltage, the duty cycle, it decreased because of we need to get 9 volts. So you can see the difference between the 15 volts duty cycle and the 20 volt duty cycle. So now let's conclude this. From the simulation results, it's found that in case of buck converter, the desired output voltage can be obtained by selecting proper values of inductor, capacitor, and switching frequency. Constant voltage can be obtained by designing a proper PI control to control PWM signal. The output voltage is constant, but it has little ripples due to switching frequency and the capacitor of buck converter. But those ripples won't affect the output voltage that much. But if the capacitance and switching frequency is increased, the ripples will be reduced. This project is successfully executed according to the function of the components implemented in the design. Thank you.